So last class we talked about, the last class we did lecture, we talked about a couple different types of energy. What were those two types of energy that we've talked about?
Kinetic and potential.
Good, good. Kinetic and potential. And kinetic means energy of an object that is doing what?
Which one?
Kinetic is the energy, yeah, has to be in motion, okay? And so potential energy, what type of potential energy have we talked about so far? Potential energy due to what?
Gravitational.
Yeah, gravity. Okay, so anything above the ground that has the potential to fall and do work on another object has potential energy. So we're going to look at our other type of potential energy today, kind of the final section with that. And we're going to look at the potential energy of a spring, or elastic potential energy. Okay? So a couple terms that we need to kind of be familiar with here in a spring is when something is static, what does that mean to us?
Not moving.
Good, it's not moving. Okay, so a static spring means that it's at rest, it's not being pushed or pulled, it's just resting. Okay, so something that has static spring status means that it's not moving. Okay, it also means that it has no potential. It has no potential energy if it's at its static position. Okay, if it is being compressed, that means we're pushing it together. Okay, we're shrinking it down. It's being stretched, we're pulling it out. Okay, hopefully those terms are pretty common sense to us. But we need to be familiar with that terminology for springs. Okay? Bless you. So when we're looking at springs, we have a different equation for the potential energy of a spring. Okay, and that is the equation there for springs. 1/2 kx squared. Okay, because when a spring is stretched or compressed, okay, so if I compress my spring, what would I expect it to do when I let go of it? Yeah, it's going to bounce out. And if there's something on the other side of that spring, what would it do to that object? Okay, let's say I have a spring that's compressed and I have something sitting right next to it. When it hits that object, what's it going to do?
Transfer the energy.
Yeah, it's going to transfer the energy. It's going to move that object, right? It's going to apply a force and displace the object, which means it's going to do work on that object. Okay, so when an object or when a spring is stretched or compressed, it has the potential to basically go the other way. Okay, so anytime we've got spring that's moving, it's got or that's being stretched or compressed, it's got potential energy. So our equation is 1/2 kx squared. K is what we call a spring constant. Okay, a spring constant. And when we think of a constant, we usually think of one number that always gets plugged in. However, that's not really the case for spring constants. Spring constants are individualized based on that spring, kind of how tough they are or how loose they are. But each individual spring has its own spring constant. All right. So each individual spring has its own spring constant, okay? And the units for K are newtons over meters. Okay, and we'll see where those units come from here in just a little bit. What do we think X might be? I can't think of the word that I want. What do you think X might be displaying?
How long it's either stretched or compressed?
Yeah, perfect. X is our displacement. Good. X is displacement. Okay, so X should probably be measured in what? Meters. Good. Meters. Okay, so X is the distance our spring has been stretched or compressed. Usually, is a spring going to be stretched or compressed a matter of meters? No. Okay, so we have to be careful when we convert from centimeters to meters or millimeters to meters, whatever it is. But you're usually not going to see a spring that's stretched a matter of meters. So you're probably going to have to do a conversion there. Okay? So now we've talked about all of our versions of kinetic and potential energy, and we're going to put them together into something called mechanical energy. Okay? And mechanical energy is the total energy of our system. Okay? And I'll walk through what these equations mean. Just go with me a little bit at a time. You're probably not going to need to write these equations down just yet. I'll give you kind of an expanded version of them. But what I want you to start understanding is that the mechanical energy is what we're really going to be looking at here. It's the energy of the entire system. Okay? At any moment, we see our total energy occurring as the kinetic energy of that system plus the potential energy of that system. Okay, so when we talk about like our roller coasters, okay, so here's roller coaster. Okay, at point A, if we start our roller coaster cart from right here, does it have all potential, all kinetic, or both? Yeah, it has just potential right here. If my cart is somewhere in the middle, okay, do I have all potential, all kinetic, or both? Both. So I have potential and kinetic here. Okay, so if I wanted to find the total amount of energy on my system, I would add together the potential and the kinetic. If I wanted to find the whole energy of my system at point A, I would add kinetic plus potential, but my kinetic would just be 0. Okay, so we're going to use all of these terms, kinetic and potential, but sometimes we might only have one of the other. Sometimes we might have both. Okay? So now we're able to look at the energy at one point in our system. It's not something that we do a whole lot. Most of the time we're looking at the energy of the system in terms of a before and an after of some sort of change. Okay? So we're going to look at the change in energies to form one equation. Okay, so we're going to take the change in energy to demonstrate to us the conservation of energy. What's it mean to be conserved? What?
Not losing.
Yeah, not lose or not to gain, right? Conserved means it's not losing or gaining energy. There's no change in terms of gain or loss. There's just transformation. So when we look at the total energy of the system before and after some change, I don't really like the way that your book describes this. Really, it's just energy initial equals energy final. Okay, so it's kind of before and after. Energy before equals energy after. I always like to put before on the left and after on the right. Okay, so you'll kind of see that when we look at this. But basically, we're talking about if we wanted to look at our roller coaster example again. Okay, at point A, we had all potential, we said, and at point B, we had both. So if I wanted to look at the change in energy, or if I wanted to find something between these two systems, I would say kinetic plus potential equals kinetic plus potential. Okay, and at the very top, at point A, what type of energy did we say we had? At point A, what type of energy did we say we had? Potential. So at the beginning, I have no kinetic energy, and I have potential. At the end, do I have both types? Kinetic plus potential. Okay, so we would be able to plug in the object's mass, whatever height it was, to be able to start solving for these things, but that's how we're going to set it up. Okay, so this conservation of energy equation has 4 terms. Okay, sometimes we'll use all 4 terms, sometimes we won't. Like in this case, we only had 3 terms. Okay, does that kind of make sense? We're going to expand those potential and kinetic energy equations even more right here. Okay. So if we wanted to look at one point on our system, like we did in that first equation, we would say potential energy plus kinetic energy equals the total energy of that system. Okay. Realistically, we're not going to use this 2-term equation very much. We're going to use the whole expanded version of that 4-term equation. Okay, we know that h is going to be our height above the ground, and we know that velocity is our speed here at that point. Okay, did those equations look familiar, 1/2 mv squared and mgh? Those are kinetic and potential energies. Okay, so we're just putting them into one. Here is our large, big 4-term equation, and this is going to be the one that we absolutely use the most in our section for this chapter. Okay, this is all 4 terms. This is kinetic plus potential at the beginning equals kinetic plus potential at the end. There's really not a whole lot of need for you to have these 2 top ones. You're just really going to want this expanded one here at the bottom. The total energy of the system and the transformation that we see. Okay, so if I have an object that is held above the ground, okay, what type of energy does it have? All potential. Okay, as it falls, what do we see happening? It starts to balance out a little bit. As it falls, is it gaining potential energy or losing potential energy? Losing. And what is it gaining then? Kinetic energy, good. So by the time that it reaches the ground, or just before it hits the ground, right, we're not thinking about when it hits the ground and comes to a stop. We're thinking about the instant before it hits the ground. What type of energy does it have? All kinetic, right? We're at that point where it doesn't have the potential to fall any further. So at that point, it's all kinetic. So I want you to make sure that you understand kind of that sliding scale between potential and kinetic. Okay? Let's try one here. Okay, so we've got our stone that's being dropped. At the top right here, what type of energy does it have? Potential, kinetic, or both? All potential. And then at this point right here, what does it have? All potential, all kinetic, or both? Both. Yeah, good, both. Okay, and why does it still have both of those types of energy? Hasn't hit the ground yet. Okay, there's still a height right here of 1 meter. Okay. So what we're going to do is start setting up our equation. We would say kinetic plus potential equals kinetic plus potential. We know at the beginning, right, on the left side, that's our initial. Does it have any kinetic energy? No, so I put a 0 in there just so I know that I've accounted for all of my terms. Okay? And then here, does it have potential energy of a spring, or does it have potential gravitational energy? Gravitational. So we'll use that equation that we have, mgh. Okay, 1/2 mv squared is the kinetic plus mgh, right? If we were dealing with a conservation of energy or a problem that had springs instead of an object that was moving vertically, we would plug in 1/2 kx squared here for our potential energy. Okay, so I'll give you that whole expanded equation here to put on your equation sheet in a second. Okay, let's see, does it give us a mass here? No, so we can't plug in anything for mass. We're just going to leave it right now at m. Okay, gravity is 9.8. Its initial height is what? 3. Okay, so we're going to keep this m here because we don't have the mass yet. We're solving for velocity. Okay, do we see where all those numbers came from? G is just 9.8. Yet, the only thing we did beside that was plug in the height. Okay, so let's go ahead and combine these equations, right, or sorry, these terms right here. What's 9.8 times 3? 28.4, 27.4? 29.4, okay. 29.4 times m equals 1/2 mv squared plus 9.8 m. Okay, so algebraically, what should our next step probably be? Yeah, I'm going to combine those like terms. So I'm going to subtract over 9.8 and the m. Subtract all those over. Which leaves me with 19.6 m equals 1/2 mv squared. So now what can I do to the m's? Yeah, I can cancel them. Okay, divide by it on one side, it would cancel it on the other. Okay, because we're left with just multiplication terms. There's no more addition and subtraction. We're left with just multiplication terms. So now from there, I would take 19.6, divide by 1/2, divide by 1/2, and then I would be left with v squared, so I would need to square root that whole answer. So 19.6 divided by 1/2. So I'd want to square root both sides. Okay, what did we get for our velocity here? 6.26 meters per second. Okay, and is our velocity going up or down? Down. Gotta put the negative in there. And remember, whenever we square root with that velocity, you're gonna have to really think about, is it going up or going down? Okay, so just, that's gonna be one you might have to put back in there. Okay. Any questions here? Okay. Very good. We have a roller coaster that's starting from rest. That's important, at the top of the hill, that has a height of 40 meters. Okay, we want to know, what is the speed of the cart at the bottom of the hill? Okay, so at the top of the hill, what type of energy do we have? Potential. And at the bottom, what do we have? At the very bottom of our roller coaster track, we just have pure kinetic, because it has the potential basically to go no farther. Okay, no farther in the downward direction, assuming that we stay on the tracks. That's the goal. Okay. Yeah. So since we only have potential at one place and kinetic on the other, it scales down our four-term equation a lot. Okay, so we can say 0 plus potential equals kinetic plus 0. Right now it's only a two-term equation instead of 4. Okay, and you don't have to write down kind of this bare bone version. I'm just kind of showing you so we have all those terms there. Okay, I do like to include the zeros. That way you know for sure you accounted for all four terms, but they just are equal to 0. Okay, so we would say mgh equals 1/2 mv squared. Okay, again, we don't have a mass given to us. The height at the beginning is 40. We want to find the velocity at that point. Okay, so here our m's go ahead and cancel right off the bat, because we have one on either side. Okay. With this one, I'm not as concerned with, it's not in a free fall, it's still moving forward, so we don't really need to include a negative here. Okay, for things that are specifically in free fall, I would look at that negative. But here, since our roller coaster is following a track moving forward, I'm going to keep that at a positive. But did we get it to come out at 28? Okay.
What do you do for V2?
For V, this right here, V squared?
Yeah.
Okay, when you divide, okay, I took 9.8 times 40 and I got 392. And then I divide by 0.5, divide by a half to move that over. Right, are you with me?
Yeah.
Okay. I got 784.
I typed 4, so
Okay, so 9.8 times 40 is 392. Then we want to divide by a half, not multiply by a half.
Right.
Okay, and then we square root that. Okay. Okay, so at the bottom it's going to be 28 meters per second. Now we're going to take this a little bit further, and we want to see at what height will the car have half of this speed. Okay? So how many of you automatically think 20 meters? Right? Halfway down the hill, half speed. I wish it was that easy, but it's not. Okay? I probably kind of primed you for that question since I even asked it. Okay, so at what height? That means we're looking at our roller coaster. We're going to be somewhere in the middle here. Okay, so what type of energy will it have somewhere in the middle? It's going to have both, yeah. So we're going to start at the top like we did before. We're going to start from there and say 0 kinetic energy plus mgh equals, now it's going to have both of those, 1 half mv squared plus mgh. We're not going to put 20 for the height because we're going to solve for this final height, right? The car is going to be somewhere in this range, but we're going to use 40 for the height because that's where it started from. So we'll use 40 for the initial height right here. What do we know about the velocity, though? But we want half the speed. What's half of 28? 14. So we're going to say 1 half m times 14 squared. So we want to find out at what height will it be moving 14 meters per second. So we're solving for height this time. This is 196.
14 squared is 196.
Okay, times a half is 98 m plus 9.8 mh. Oops, this is 392 m on that side. So now I've got 392 m equals 98 m plus 9.8 mh. So I need to combine these like terms. Minus 98 m minus 98 m. Okay. I'm going to move it up here. 294m equals 9.8 m times h. Okay, we're solving for h. Now our m's will cancel. We divide by 9.8. We get 30 meters. Right here, 14 squared times a half. I got 98 for that. 98 times m. Okay, so that means it's only traveled 10 meters downward, but it's already picked up half its speed. So it picks up most of that acceleration right at the beginning. Okay. Questions here? Okay, so we talked about how if we've got a spring, we're going to substitute the mgh in for that spring potential energy equation. So I'll go ahead and give you the full equation before we start plugging it in here. We would say 1 half mv squared plus potential energy of a spring, which is 1 half kx squared, equals 1 half mv squared plus 1 half kx squared. Okay, so if you want to put that full one on your equation sheet, you can. This is a big clue right here, this k. That's going to tell us that we're working with a spring. Okay, that's the only time you use this equation is when we're working with a spring. All right, so now let's start looking at this. A dart is pressed against a spring. It's compressed 6 centimeters. Detaches from the spring. What speed does the dart acquire? Now, you don't have to write this down word for word, just get down the main stuff. You could admire my artwork here at the bottom. Okay, that's all I got. Okay, so we see the compression of this dart, right? Here's my dart. And it's compressed a total of 6 centimeters. Okay, when it releases, or when it gets back to its equilibrium point, which means this is its equilibrium point right here, that dart releases. Okay, so do we see kind of what's happening there? Yes, no? Okay. At this point, at the beginning, when it's compressed, does it have potential or kinetic or both? potential. All potential. At this point, when it's at its equilibrium point now, or it's at its static point, what does it have? Just kinetic. And this is why. Okay? It's still in motion because that spring is still going eventually to spread all the way out. But right now it's in the process of that. So that dart detaches. It happens to detach right when it gets to its static point. But that spring, after being compressed 6 centimeters, is still going to stretch 6 centimeters before it comes back to that static point. Okay, so it's still in motion. It's going past its equilibrium point. Okay, but at this point, when that dart releases, it just so happens to be at its equilibrium point, which means that here it's got all kinetic. Okay, when the spring reaches a full stretch of 6 centimeters, what type of energy would it have like at this point right here? When it reaches its full stretch, before it starts to go back, what type of energy would it have?
Potential?
All potential. Okay, so just something to think about. So we're at this point right here. Okay, it's moving through its equilibrium point, but the dart has detached. So here we've got all kinetic. Okay, so as we look at our 4-term equation, this initial kinetic energy is 0. Okay, we have potential energy. We've got kinetic energy. That spring will transfer to the dart. Okay, that's why we're looking for the speed of the dart, because that spring will transfer all of its kinetic energy to that dart. And then we said it has no potential at the end. Okay, so we only have to use 2 terms here. Okay. My displacement here, my x value, needs to be converted from 6 centimeters to meters. So that's where that 0.06 came from. Don't forget to square. Okay, a lot of you will forget to do that. Sorry.
When did you get the 0.45?
I took 0.06 squared. Just the 0.06 is squared, not the whole term. Okay? So we just are squaring that x term, not the whole 1/2 kx. All right, be careful with that. And we get 0.45. We're going to divide over that 0.05 and then square root. So I got somewhere in the 3 meters per second range. I think you can go ahead and do this one on your own.